Okay, we're going. So the topic for today is basically how does the signal get into the RF coil? But it turns out that's pretty much the same. It's completely symmetrical, so you can also think about how the RF coil generates a magnetic field that gets into the brain. So it's sort of coming from the precessing protons, out to the coil, and then the coil putting an oscillating current into the coil, and then making the protons precess. So those two things are very similar. So before I do that, I'll just do one final review of the block equation, but also mention the rotating coordinate system, because this is going to be relevant to understanding the signal that comes out, because it turns out the signal, surprisingly, the signal that comes out of the coil after it's been through the initial hardware is actually in the rotating coordinate system. So that's not just kind of sort of a convenient way of thinking about it. It's actually that's actually what the signal is. So we'll talk about how we get that. And so just to review the block equation and put up a diagram that I had up there before, if you just imagine you've got the B field here, you've got three parts of the block equation, and so the three parts were, so this is the B0 field, and then you've got some additional field added on there, so this guy is the B1 field, which is what we're talking about. That's what we're talking about today. So that one's perpendicular to the B field. And then, and so those add together, into the effective B, the full B field here with no 0 or 1 on it. And then we talked about the three parts of the block equation. And so the three parts of the block equation were, you had the, whatever the magnetization, the local magnetization vector is. So that's whatever in a particular part of the brain. What is the in that little voxel? If you sum up all the precessing protons, what is the vector that you get? And then we had three different parts of the block equation. So the first part was the precession part. That was sort of causing it to go around that way. That was the part that comes from the M cross B. So that's that part. So there's the M cross B part. And then we had a T2 decay part. And the T2 decay part was perpendicular to that, and it was heading toward the center of the circle. So there was another component, and that component came from the M XY over T2. Oops, wrong color. Colorful hands today. So that was the M XY over T2 part. So that was this guy, and that was this is a perpendicular. So it was perpendicular, and then finally we had the T1 regrowth part, and that part was also perpendicular. So they're all perpendicular to each other. And that last part was the MZ minus MZ0 business, over T1. So, so that guy goes there. So those are the three parts, and then the final answer is this is, the update. So this is the full, that's the full dm dt. So what we want to talk about today is mainly having to do with how the B1 affects this, and then how this precessing thing actually gets into the coil and generates a signal in the coil. So so the reason I put this all up again, I didn't add anything from what I did last time. The reason I put it up was to talk about the rotating frame. And so what's the rotating frame? 1 second. Get out of the. So the rotating frame is this idea that sort of simplifies your picture of this m vector. So in real life, it's flipping around at 123 million cycles per second, very rapidly, and then at the same time, while it's flipping around, it's actually maybe changing in length and maybe changing its angle relative to the B0 field. And so one primary simplification, if we sort of look at it in stages, so if we just start off with just the precession part, so here's our coordinate system, and we just start off with just the precession part. So here's a guy just precessing around at 123 million cycles per second. So here's the B field, and here's the M. Now, when we put this into the rotating coordinate system, the rotating coordinate system means we're spinning around at 123 million cycles per second. What happens? So what happens is you just stop it in its tracks. So basically, you've still got the B field here. So this is just precession. And this is a rotating coordinate system. So sometimes this is called the lab frame, the laboratory frame, laboratory coordinate system, and this is the rotating frame. So there's the B0 field. There's the B0 field. So what does it do to the B0 field? It effectively makes the B0 field 0. Because now we've just stopped the M vector in its tracks. So the M vector is completely stopped. It still might change angle, but M vector is stopped. Now, it might move slowly, and what does that mean? That means its frequency is slightly different. It's slightly different than our rotating coordinate system frequency. So if we're not rotating at the right speed, then we'll see conversely, if the M vector isn't precessing at the speed of our rotating coordinate system, we'll see it slowly move. That's an important, you might want, that sort of at first doesn't make any sense, like why don't you just make it the right speed? But what it has to do with is changes in the phase of the rotation. If it's moving in the rotating coordinate system. Okay, so this implies, M is stopped, that implies, that B0 equals 0. So we've just stopped it. But the interesting thing about this, the reason why it's valuable to think of it this way, is that if we apply a B1, so which is what we're going to talk about today, sort of add B1. So it's hard to think about, when you think about it, with the precession going on, and then you've got this B1, here's the real life situation. You've got a big B0, and then you've added on a perpendicular component, but that perpendicular component just adds to this guy, and so what happens is that this long B vector is wiggling that way, and then trying to figure out, like, how does that actually affect all these guys? It's kind of hard to keep it all in mind, and so it's easier when you do it this way, because if we apply, for instance, the B1 field to the stopped vector, so now the vector is stopped, it's just sitting there stopped. And so if we apply the B1 field now we can just see the B1. We've sort of screened out all the wiggling, and we just have the B1. And it turns out that this original part of the block equation, the M cross B, still works. It still works. And so how does it work? Well, like, remember how so basically this vector right here is a vector that's perpendicular to this guy, and it's also perpendicular to that guy. It's a little vector. That's what the cross product says, is get a vector that's perpendicular to both of those. And then we paste it up here. This is the dm dt that tells us where we go next. That operation works in this case. So it works in this rotating frame where this vector is stopped. It still works. And so how would it work here? Well, what is it going to do if this is the M vector here? There's the M vector and there's the B vector. What it's going to do, it's going to give you, if this is the direction of the B field, instead of being up, say it's around the x-axis. So here's the x-axis, y-axis, z-axis. What is it going to do? It's going to rotate. It's going to rotate this. So that'll be you can work it out to convince yourself that that's the right answer. But that's the dm dt. And so you can think of, so you can use this, so here's one handy way of thinking about it. maybe yes, maybe no. Imagine you put a screwdriver down from sort of the opposite direction of the B field, and you're screwing in a screw. That's the direction that you go. So here's the B field. We sort of like stick the screwdriver in the opposite direction from the direction of the B field, and we sort of like run the screwdriver to screw a screw in, and that's the direction of the cross product. That's just another sort of mnemonic way of remembering it. So basically, but this is the important thing. So that M cross B still works, and so you can think of flipping the stopped magnetization using the same logic that you use for predicting the precession. So that's the real bottom line for why you want to sort of think of the rotating coordinate system. And there's another thing that we'll talk about later. What about, this happens all the time. What if we stimulate at the wrong frequency? So say, these guys are precessing at a certain frequency like this. And what if we stimulate these guys, at the wrong frequency? They'll still get stimulated to some extent. And you can think of that in the rotating coordinate system. There's a tricky way of thinking of it in the rotating coordinate system that helps you sort of reason about it. So I won't talk about it now. I'll just introduce the topic that this is a problem because everything's always off resonance. It's like T1 weighted. There's always off resonance. So it's something you have to actually pay attention to really sort of understand how the signal comes about. Okay, so that was it was 20 minutes of intro. So let's start with, let's go ahead and start with the coils. So how do the coils actually work? So for this, we have to sort of think about how magnetic fields and electric currents work. So there's three things to keep in mind. There's the electric field, that's like static electricity. Then there's an electric current, that's different. That's actually charges moving. And then there's the magnetic field. So don't mix up those. There are three different things to keep in mind: electric field, magnetic field, and then electric current. And so the principle of the coil has to do with the relationship between the electric current and the magnetic field. And the relationship is that if you move some current, say through a wire, it makes the magnetic field. But equivalently, if you move some magnetic field past a wire, it makes a current. So that goes both ways. So what we're going to talk about is just how that causes a current in the coil. And so if I draw a nice big bore here, not going off, yeah, looks good. And then here's the bore, and we'll put a huge head in the bore so that I can have space to draw the coil. So there's a happy person. Happy to get scanned. There's their alien-sized head. Okay. So how does the coil work? So let's just let's start with a loop coil. So a loop coil is the simplest coil, and if we took apart our 32-channel coil, not that I've taken it apart and voided the warranty, but say if one were to take it apart, what would you find inside? You'd find a bunch of loops. And so each of the coils in the 32-channel coil is in fact just a loop. And so so let's just draw that loop. So I'll draw a loop here. And then I'll have some twisted pair coming out. So why do you twist it? Well, the reason is because we don't want a magnetic field to come out of this part. And it turns out, if you just take two wires and twist them, and then have current going opposite directions in those two wires, because the current will go in one wire and then come back the other one, the twisting will sort of cancel out all the magnetic fields that are given out of that. But conversely, they will also prevent you from picking up magnetic fields. So say there was some magnetic fields that were moving around here, that has the potential to illustrate induce a current in here that you don't want, because you just want sort of current coming from, you want current that was induced by magnetic fields in the head to come out. So that's the twisted pair. So now let's just consider what happens. We left out the capacitor. So there's always a capacitor in a coil, and a capacitor. So what's the capacitor for? The capacitor it's the right value of capacitor so that capacitor will get charged up and discharged by an oscillating field. So typically if we're either trying to record a 123 megahertz signal, or we're trying to actually energize the coil in order to inject 123 megahertz into the head, we want the capacitor in there, because if you get the right setting of that capacitor, as the current goes back and forth, it'll charge, all the charges will build up on one plate, and then they'll flip, and then they'll build up on the other plate, and they'll sort of go back and forth exactly at 123 megahertz. And then it won't pick up other signals that are coming at different frequencies because the capacitor isn't the right setting for them. So that's how the coil gets tuned to pick up a particular frequency. So Okay, so now let's just consider, so it's a break in the circuit, but the current, you can think of the current as sort of like going, it's as if the current was going back and forth, but actually what's happening is the current's going this way and the charges are piling up on this, and then charges are leaving this side. So it looks, even though there's a gap, it acts as if there was a current going back and forth with that capacitor in there. So let's just take an example of, what happens if the current is, say, going, this direction in the coil. So that means that the current is going to, if your thumb is the current, your thumb comes up like that, and then the fingers will point in the direction of the magnetic field. And the magnetic field will go one direction through the coil, but then if you consider it going on the outside of the coil, it's going to be going the other direction on the outside of the coil. But right in the middle of the coil, in this case, the current is going to be coming out at you. Sorry, out at you. It's going to be coming out at you if the current is going up. And so what does that look like? That looks like not the current, the magnetic field. So the magnetic field is going to be sort of coming out at you like this. So what is that? That's when the current is at its maximum. That will be our B1 vector. When the current is going this direction around the coil. And then 120, so 123 millionth of a second later, the current will be going in the opposite direction. And when it goes in the opposite direction, what's going to happen is the magnetic field will be pointing out this way. Pointing out the opposite direction like that. And so what will happen is the magnetic field right in the center of the coil and sort of on an axis through the center of the coil will just be going back and forth, left, right. So this is, left, right. So it's a vertical coil. So this was a vertical coil, so vertical, Y direction coil. And the magnetic field that it generates is left, right. And it's, typically we're applying something that looks like a cosine to it, a current that's going, from positive to negative, positive to negative, positive to negative. And so how can we write that out? So we can describe that as a linearly, as opposed to circularly, linearly polarized field. And so the way we write that out is we write out the B vector, the B1 vector, at a moment in time is equal to the strength of the B1 field, so that's just a number, sort of mean strength. So here, let's just put that, so this is the mean strength, because at some points the strength is actually zero. Right when it changes to the opposite direction, the strength will be zero. So that's the mean strength. And then times a cosine of, I'll leave that out, of omega t. So omega, remember, is the frequency. So this was, cycles per second, or this is radians per second. So radians per second, and then times seconds equals, so what does that equal? That just equals radians. So that's just an angle. And the cosine of an angle, what's the cosine of an angle? Well, that just, the cosine is, it goes down like this. This is like 0, 360 equals 2 pi. So, and that it goes from, -1 to 1. So the output of this is, -1 to 1. So we put it in, it's between -1 and 1. The mean strength is just a number, some kind of number. And so then we still have to have a direction. And so if we have a vertical coil, the direction is going to be the x direction. So we multiply it by our x unit vector. I could have written it out as I. That was the same thing that we wrote out as I before. So this is, unit vector. So that unit vector means like a vector of length 1. So this guy gives it the direction. This is the angle at any instant in time. So as time keeps ticking up, that angle is going to be changing. And then we take the cosine of that angle, we get something between 1 and -1, and then we scale it by what the mean strength is, and that tells us what the... So that's a linearly polarized field. So that means it just goes back and forth along one direction. So what is it actually, adding up to? So what this means is you've got like a giant, I'll draw it the other way since we got the magnet sort of. So you've got this giant B1 field, B0 field, and then we've got on top of it, we've got this B1 field, which is going back and forth. And so basically the B0 vector is just wiggling back and forth. And this is the B1 part of it. So we've sort of gotten rid of the B0, and we're just considering the B1 part. So that's what's actually happening. So it's just causing, let's just draw a coordinate system again here. So here's the y direction, here's the z direction, and then here's the x direction. And that's the same, remember that's the same coordinate system we were drawing before when we drew it out as z over here and x and y. That's the same. If you just rotate that sort of 1/3 of a revolution, you'll see it's the same. So, okay, so this is our standard loop coil. So this, now, when you think about this, it's sort of like, how does this work? Because there's precessing protons in there. So what are the protons in there? Well, they're precessing around the xy axis. So they're sort of like going around, around this axis right here. So they're going around that xy axis perpendicular to the z. So you can think of them as either sort of precessing this way, or you can say like, well, we're just getting rid of the z component, just consider the xy component. So these guys, so here's one of those guys, and it's rapidly precessing around the xy axis. So how does that work when we just hit it with just a straight line? So we're just hitting it with something that's going back and forth. Turns out that actually works, strangely. So you've got sort of protons spinning, and you just hit them from one side, and you can sort of get them. You can actually get them to sort of line up with each other, so that you'll actually get a coherent signal out of them, even if you're just hitting them just completely from one direction. It still works. It's, to understand it, we have to sort of work through the quantum mechanical equations. But you could sort of think of something similar if you have like, if you just think of a swing, and you just kind of take a sledgehammer and slam on the swing, it will start swinging and oscillating, even if you don't hit it at the right time in the cycle. It will still work. So that's linearly polarized, but typically for the most part, and it works the other way too. So if you think about, say, so here we were talking about injecting a current into the coil that makes this field perpendicular to the coil, and then how do we then cause the protons to precess? But it works the other way too, and the other way is the protons are precessing. They're wiggling in there, going around perpendicular to the z-axis, and they will then induce a current in the coil. So those two are sort of the two converses. You can sort of think of it either way. And what kind of a current will you get out of the coil? Well, you'll essentially get an oscillating current. So essentially, as the proton the proton magnetic field sort of rotates, if you work through kind of the right-hand rule, you'll see that you'll get exactly the same thing that you would get if you're doing it sort of like injecting the current. So basically, the current will just go back and forth in the coil as a result of just some circularly rotating proton magnetic fields. But a lot of times what we want to do is use a circularly polarized field. And so how do we do that? So to do this, we need a combination. One straightforward way to do it is just add another coil. So if we added a coil like this over the top of the head, put a capacitor in it, over the top of the head, and then there's a little twisted pair coming off. And say we put where are we going? Yeah, so if we're going that way, say we put a cosine into this guy, but a sine into this guy. Then we would get a circularly polarized field. And so how does that work? So this coil is going to make a magnetic field that's going perpendicular to the one I drew here. So this coil is going to make one that's going this way. It's going up and down. So it's going to go up and down through the head. So if we add those two to each other, these are vectors, and so if we say we add a little bit of the vertical one to a lot of the horizontal one, then we'll sort of tilt the horizontal one up a little bit. And if you put a cosine and a sine, you can exactly cause a rotating field that doesn't change length to be injected into the brain. And vice versa, if you have a rotating field in the brain, it will generate a sine and a cosine coming out of the coil. So that's a circularly polarized field. And so we can write that one out. So this is B1 ln. We could write that one out in several ways. And so we're going to introduce a way of writing it out that uses complex numbers, because we're going to do this repeatedly. So this is as good of a time as any to do it. And so now we've got the amount, our average amount of the B1 field, but we're now multiplying by a cosine of omega t times the x unit vector plus the sine of omega t, or I'll put a minus here, minus the sine of omega t. You'll see what the difference between a minus and a plus is, times the y unit vector. So that's basically a rotating B1 field that doesn't change length, stays the same length all the time, whatever, which is determined by this B. So what does that look like in real life? Well, that's the one I was drawing before at the beginning of the class. So it basically looks like, something that's rotating around like this. It's got a rotating vector on it, tacked onto the front of it. And so it's, going around in a circle this way. And so it could be going the other way. It depends on, whether you have a plus or minus. And so here's that, sum. This is the B1, B0 plus B1. Okay, so what's another way to write that out that is commonly used? And so that other way that's commonly used, uses complex numbers. So we've got some space in the middle here for some complex numbers. So complex numbers, they're basically, you can think of them as two-dimensional numbers, and this is kind of a two-dimensional system here. And so the way that you typically write this out is using this this thing, sort of the e to a complex exponent. And so the very first time you see this, if this is the first time you see it, that your first sort of reaction is, that's not right. It's like, I can understand a real component, but what does it mean to have a complex exponent? It just sort of doesn't compute. But the way to think of this, whenever you see an e with a complex number in the exponent, so we talked a lot about, e to the minus t over t2. That's a real number. This thing is different. So that's a real negative number in the exponent. That you can understand. That's like 2 squared or something, or 2 to the 1.5 power. This thing is different. So this thing is actually a two-dimensional number. It's a complex number, and it's one way of thinking of it, you can think of it as a way to turn a linear variable. So this guy is a linear variable. So what do we mean by that? That's an angle. Well, an angle is a linear variable because it just can get higher and higher. So you can go like, 50 degrees, 300 degrees, 700 degrees, 12,000 degrees. That just keeps going up. Angle can just keep going up. And, if you look at these equations right here, after like a second, the angle that you get out of here is really huge. If you've got a frequency of 123 million cycles per second and you're multiplying by 1 second, this number is 123 million. That's a really big number. But it's an angle. It's still an angle. 123 million is still an angle. 123 million radians is still an angle. So that's a linear variable. But the thing you get out of it, when you raise it to that complex power is a circular variable. And so how to think about this circular variable? So it's a circular variable, and a circular variable that has two components. It's a complex number, so it's got a real part and an imaginary part. And so one way of thinking of that thing is just to plot it out on a circle on a plane. So here's the real axis on the plane. Here's the imaginary axis on the plane, sort of x and y axis. So real is x, and imaginary is y. So if we plot that out, so here's a radius of 1. So it's a radius of 1. And so this thing actually represents a complex number with amplitude 1. So that's what that means. So if you just see an e to the I anything, so e to the I angle, translate in your mind into a vector with a length of 1 and some angle, and the angle is what you have in that theta there. So So here's that angle. So here's the angle theta. And then here's the imaginary part, and here's the real part. And so we can either, so you can think of this just as a method of converting between polar coordinates, angle and length, and Cartesian coordinates, which is like the x, which is the real, and y, which is imaginary. And so what does it mean? So a lot of times you'll see e to the minus I. What does that mean? What is e to the minus I theta? Well, that's just a minus angle. And so what's a minus angle? Well, that would just be, what if you just went like this? So here's minus theta. And minus theta is going to have the same, it's minus theta have the same real part. The real part of the x part will be the same, but the imaginary part is going to be minus I. And you could also think of this as e to the I minus theta. That's another way of thinking of it. So that's all that a minus up there means. It just means go the other way. Just take a negative angle instead of a positive angle. Okay, so it's common to write out this mess with, and if you look at you can see why complex numbers are related to sine and cosine very clearly, because if this, so what is what is this length of this real part here? Well, that real part is the adjacent side of the right triangle. So there's a right triangle, and so what's the length of that? It's going to be the cosine of this angle times the hypotenuse. The hypotenuse is 1, so it's just going to be the cosine. So basically, this length just equals the cosine of the angle, and this length just equals the sine of the angle. So, and that's exactly what we have down here. So one way of writing this out that you'll see all the time is we just take b1, still a real number. So this guy is just a scalar, just a real number. And we multiply that by this, e to the minus I omega t. So now we got two things there, omega t instead of just theta angle. But remember, omega t is just it's just a way of finding an angle at a particular time. So that this whole thing just boils down to an angle. So, yeah, so this guy's just, this guy is an angle. Now, last but not least, if you see something like this in an equation, always think back. So this guy's complex, right? This guy is real. So when you think back to what does complex multiplication do? So complex multiplication, remember, you multiply the amplitudes, and since the amplitude is 1, that means we're just multiplying by 1, so that means we're not going to change the amplitude of this real number. And then we add the angle. So whatever angle is in here, we just add it onto this two-dimensional vector. So when you see something like this, you should think it's a completely different mental operation than something like this. So something like this, when you see something like this, you're thinking, oh, exponential decay. That means something that falls off. When you see that, you think that. That's what should pop into your mind, an exponential decay over time. When you see something like, e to the minus I omega t, now you have to think something completely different. What this means is add this angle, or subtract that angle if it's a negative. That's the meaning of this. So this means, they look the same, but they're completely different. So this means like, exponential decay. This guy means, modify angle. And there's going to be a lot of modifying angles. And we'll go over this again and again because this is how the Fourier transform works. It involves things that are like this, these length 1 vectors with angles in them. That's the Fourier transform is a complex addition of a bunch of those guys. Okay, so in the last minute, let's just, I think I'll just sort of leave it there. But this is a way, this kind of notation of multiplying an amplitude times this complex amplitude 1 number. So this is like, you can sort of think of this thing as a pure angle. It's just an angle with the amplitude always 1. So whenever you operate using one of these things, you don't change the amplitude of this guy. You just kind of like change its angle. But that's exactly what we're going to often do. Whenever you have any kind of oscillatory process that's, where you come back to where you were before, like if you go all the way around the circle, you come back to where you were before, that's why you always end up with these complex numbers to sort of help us think about it. So I'll just say one last thing about the signal to noise of these coils. So one of the things about RF coils, you might know that, why do we have a 32 channel coil? It's got smaller coils in it. And you might have had some idea, well, if you have a 64 channel coil, there's even more coils in there. They could be smaller. And so you have an even better signal to noise. So why is that? It turns out that it's because smaller coils pick up less noise from other parts of the brain. So if you have a small coil, what happens is it will pick up a bigger signal right next to the coil. And then, like from the neck, it won't pick up as good of a signal. So that's why the signal to noise of a small coil is better. Now, if you think about, say, like an antenna, since we're picking up a radio wave, it's a radio wave that's about the same frequency as an FM radio station. So we're picking up this FM signal with our antenna here. In general, a bigger antenna is better. And in fact, you've got a body coil in there. Remember, there's the body coil that you use to transmit, which is a really big coil in there, body RF. And that coil, that's a big antenna. And that's a great antenna, and it would actually pick up just fine. So that's not the reason why small coils have a better signal to noise. They have a better signal to noise because they see less of the neck. So why is the neck a bad thing? Well, atoms are throughout your entire body are just wiggling around, and as they wiggle around, they generate little radio waves. And so just that little thermal motion of atoms just wiggling around in your head is going to make noise in the coil. And if you use a smaller coil, it will pick up the same amount of signal from the part of the head that it's sitting over as the RF coil would. So the RF coil would be just fine for that part of the head because radio waves propagate through space and they get out to the RF coil no problem. So it picks up the same signal that the big body coil would pick up, but then it doesn't pick up the signals from the neck, which is the part that we don't care about. It's just some thermal noise in the neck. So that's actually the reason why it's advantageous to have a smaller coil. And we still probably have another doubling of signal to noise from making coils smaller so that they get closer to the head. It's kind of an engineering mechanical problem. How do you make a little coil that sits right next to the head that doesn't break when you use it on a bunch of people. It's easier if you just put it in a hard shell, and it's a little bit bigger, but people have different sized heads, and so what you really want is some kind of contraption that allows you to bring the coils right up against the head. That would double the signal to noise again. It would make our 3T magnet into a 6 Tesla magnet. So, okay, so let me just stop before we overrun. So David, could we stop the recording?